Okay, so we've all heard that classic rule, right? Energy can't be created or destroyed. But what if I told you that simple law is stranger and way, way deeper than you can possibly imagine? It's this incredible thread that connects something as simple as the warmth in your hands all the way to the very origin of the cosmos itself.
I mean, really think about it for a second. A spinning top that eventually wobbles to a halt. A car that brakes and comes to a stop. Anytime something is moving, it eventually stops, usually because of friction. And it really feels like that energy of motion just disappears. But the universe is a much stricter accountant than that. So where does the energy actually go?
And this right here is the fundamental rule. That energy of motion doesn't just vanish, it simply changes its costume. When you rub your hands together, the kinetic energy from that movement is transferred. It transforms into thermal energy. You feel it as heat. But the total amount of energy in that system, it stays exactly the same.
Now, this isn't just a guideline or a suggestion. It's a law. The law of conservation of energy. And it is shockingly universal. I mean, it governs everything from the tiniest interactions to the largest cosmic events. From a kid's toy to a star that's literally exploding. It's one thing to just state a rule, but the real magic in physics, the fun part, is understanding why that rule even exists. Why can't the universe just, create a little bit of energy out of thin air or lose some along the way? The answer is honestly one of the most elegant and beautiful ideas in all of science.
So the secret, the deep, deep reason for energy conservation has surprisingly little to do with energy itself. Instead, it's all about a concept you're already very familiar with: symmetry.
This really expands our whole idea of what symmetry even is. We usually think of a shape, right? Like a circle. It's symmetrical because you can rotate it by any angle and it still looks exactly the same. But what if this concept also applies to the laws of physics themselves?
Just think about this for a second. It's a simple but profound fact. The laws of physics don't change over time. The force of gravity works the same way today as it did yesterday and as it will tomorrow. An apple fell from a tree in precisely the same way for Isaac Newton as it does for us. This consistency, that is a symmetry. It's called a time translation symmetry. The rule book of the universe is the same day in and day out.
And here it is. This is the crucial point, an absolutely incredible insight from the brilliant mathematician Emmy Noether. She showed that symmetries aren't just pretty concepts. They are the reason for conservation laws. They are the enforcers. If a law of physics has a certain symmetry, then something must be conserved. It's not optional.
And this is the direct result. Because the laws of physics are the same at all times, that's time symmetry, then energy has to be conserved. And because the laws are the same everywhere in space, that's space symmetry, then momentum has to be conserved. It's amazing. They're two sides of the same beautiful coin. One directly implies the other.
Okay, but does this supposedly unbreakable rule ever bend? I mean, the quantum world is famously weird. It's a place where the classical rules we're used to often get a total rewrite. So, can we find a loophole down there?
And at first, it looks like it. So according to Heisenberg's uncertainty principle, the universe can essentially borrow a tiny bit of energy from the vacuum to create a particle-antiparticle pair, just as long as it pays that energy back almost instantly. For a split second, it really does look like energy conservation is being violated. But here's the critical difference. In our everyday classical physics, energy is strictly conserved at every single moment, no exceptions. But in quantum physics, things can get messy in the middle of a process. The key, though, is that the books have to be perfectly balanced between the start and the end. The total energy is still strictly conserved overall.
So yeah, the law holds, but the journey between point A and point B can take some very strange detours. This is actually the principle behind phenomena like Hawking radiation, where these quantum fluctuations right near a black hole's event horizon cause it to slowly radiate energy away. The process is bizarre for sure, but the universe's energy budget remains perfectly balanced in the end.
So let's zoom all the way out. If energy conservation is the ultimate law, how in the world can we apply it to the biggest question of all: where did our entire universe, with all of its stuff and all of its energy, actually come from?
Now this is a truly wild but also really compelling idea. What it suggests is that all the positive energy that we see, stars, galaxies, light, all of it, is perfectly canceled out by an equal amount of negative energy. But
Where could all this negative energy possibly be hiding? The late, great Stephen Hawking offered this brilliant analogy to help us wrap our heads around this idea. He asked us to just imagine a person who wants to build a hill on a piece of land that's perfectly flat. So you start with flat land, which represents 0. To make your hill, that's the positive energy, you have to dig a hole, creating a deficit. That's the negative energy. The dirt from the hole then becomes the hill. So you see, the positive hill and the negative hole, they perfectly cancel each other out. You've created something from nothing without ever breaking that fundamental rule of 0.
In this cosmic analogy, all the stuff, all the matter and radiation in our universe, that's the hill. That's the positive side of the ledger. And gravity itself, the curvature of space-time that holds everything together, that is the hole. That's the negative side of the ledger.
So if you could somehow put the entire universe on a cosmic scale, adding up all the positive energy of matter and all the negative energy of gravity, the grand total might just be 0. The ultimate balanced budget. A whole universe from nothing that cost absolutely nothing to make.
So a simple, unbreakable rule that explains why your hands get warm when you rub them together also gives us this stunningly elegant explanation for how an entire cosmos could just burst into existence. The law of conservation isn't just a rule for physicists to follow. It might just be the creative principle of reality itself.